Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fourth part of mechanical oscillation. At the end of this part, you are going to be able to analyze the energy graphs of undamped free oscillations obtained by a horizontal elastic pendulum. You should remember the ideas that we have taken in the first three parts, especially that energy is constant, amplitude is constant, the time equation is x equals to xm sine omega 0 t plus phi. To study the energy of a simple harmonic oscillator, we first consider all the forms of energy it can have. We know from the existence of the spring that the energy stored in the deformation of a simple harmonic oscillator is a form of elastic potential energy. Due to motion, there is kinetic energy, and in some cases, if the motion is not horizontal along the gravitational potential energy reference level, then gravitational potential energy exists. Consider the horizontal elastic spring, whose motion is a free undamped simple harmonic. The energy oscillates back and forth between kinetic and potential energy, going completely from one to the other as the system oscillates. To observe this exchange, it should be clear that when x is maximum, plus or minus x maximum, v then is 0, thus the kinetic energy is 0. Finally, the elastic potential energy is maximum and it is half k xm squared. While if x is 0, it means that V is maximal, and thus kinetic energy is maximal and the potential energy elastic is 0. We can see that there is alternating energy exchange between kinetic energy and elastic potential energy, where mechanical energy makes no change. Let's interpret this exchange. From the equilibrium position O to position A, the motion starts with kinetic energy. As the object moves to the left, the kinetic energy decreases and it is converted to the elastic potential energy by the spring. The velocity becomes 0 when the kinetic energy is completely converted. When the spring returns back, the elastic potential energy is converted to the kinetic energy, becoming entirely kinetic energy at the equilibrium. It is then converted back into elastic potential energy by the spring when reaching point B. The velocity becomes 0 then when the kinetic energy is completely converted to the elastic potential energy. Again, from B to O, the elastic potential energy is converted to kinetic energy at equilibrium where the velocity is maximum. Since we are dealing with a simple harmonic motion, then the mechanical energy is constant during all this conversion. The variations in energy can be studied either as a function of time or as a function of x. We are going to start with the study of energy as a function of x. The equilibrium position of the center of mass G of the block of horizontal elastic pendulum is the origin of the x prime or x axis. The curves show the variations of the mechanical, elastic, and kinetic energies as a function of the abscissa x, where x lies between minus xm and plus xm. What do you think? Have a deep look to this figure and try to match the curve with the corresponding form of energy. Mechanical energy is constant because it is conserved. Then it is the red curve, which is horizontal straight. The elastic potential energy is of the form half k x squared, so its graph should be parabola. This energy is 0 when x equals to 0, then it passes through the origin. The kinetic energy then is the mechanical energy minus the elastic potential energy. Then it is of the form of x squared and it is parabola. We mentioned before that at the extreme positions, the kinetic energy is 0. Then it corresponds to the blue curve. Note that for x equals to half xm, the potential energy is not exactly half the mechanical energy. Why do you think? It's because the elastic potential energy is not a linear function. It is half k x squared. The same for the kinetic energy. It is not linear. Now, in the study of energy as a function of time, remember in the whole study that x equals to xm sine omega 0 t plus phi, and it is represented as a sinusoidal function that varies between the positive and the negative values. Let's make the start with the mechanical energy. We are through with the idea that mechanical energy is conserved. And mechanical energy is conserved, it means that it is constant at any time. And because the friction is negligible, then it is represented as a straight line. Then the elastic potential energy. Its function is half k x squared. So replace x by its expression xm sine omega 0 t plus phi. This can be written as half k xm squared into the square of sine omega 0 t plus phi. But half k xm squared and the sine omega 0 t plus phi squared are positives. So to represent the elastic potential energy, it has a maximum value half k xm squared. At t equals to 0, x in the graph is maximum, thus it is a positive function all the time and represented as such. Note that if at t equals to 0, x was 0, then the elastic potential energy should start from 0. Finally, the kinetic energy. The kinetic energy is half mv squared, where v is the derivative of x. So we can write it as half m into the square of xm omega 0 times the square of cosine omega 0 t plus phi. The same, we can find that it is positive and always positive, so its curve is totally above the horizontal axis of time, where its maximum value can be written as half omega 0 squared xm squared. And for x equals to 0, we can find that at x equals to 0, the potential energy is 0, thus the kinetic energy should be maximum. While it starts from maximum x, it means that v is 0 and the kinetic energy starts from 0. Whenever one of these two energies, elastic or the kinetic energy, is 0, the other is maximum, and all the time is equal to the mechanical energy. Note that kinetic energy and elastic potential energy are periodic, and it's obvious from this graph. While this period t energy is equal to half of the proper period t0 of the x function. Let's end with an application. An appropriate device can be used to visualize the variation of energies, the kinetic, elastic potential, and the mechanical energy of a pendulum system S, R, and Earth. Neglect all friction. So, given that x equals to minus xm sine omega 0 t, t0 equals to 2 pi over 10 seconds, and at t0, the velocity equals to minus v0 I vector, where v0 all the time positive. First question. Indicate with justification the form of energy corresponding to each of three curves 1, 2, and 3. Pause the video after each part and try to think of the answer. The graph here represents the variation of E as a function of time. We start all the time with the mechanical energy, which is conserved since there is no friction. So it corresponds to number 1, the horizontal line. At t equals to 0, v0 is said to be not 0. Then the kinetic energy corresponds to 2, which starts from 0.1. Finally, at t equals to 0 second and replace this value in x function, then we can find that x0 is 0, so the elastic potential energy should start from 0, and 3 is the one for elastic potential energy. Referring to the document above, indicate the value of the period t of the energy of elastic potential energy and deduce the relation between t and t0. Graphically, it's obvious that the period is 0.314 seconds. Then, if we divide t by t0, which is 2 pi over 10, then the answer is half. So, t0 equals to 2 times the period of energy. Part 3, write the expression of the mechanical energy EM0 in terms of m and v0, then deduce the value of the speed v0. To solve this part, just start with the expression of the mechanical energy at t0, then the mechanical energy EM0 is E0 from the graph, and at the same time, its expression is half mv0 squared plus half kx0 squared. But they want us to find it in terms of m and v0. So check the answer. At t equals to 0, we have x equals to 0, thus the elastic is 0. Then the mechanical energy EM0 is just half mv0 squared. Now, how can we deduce the value of v0? Since we know that the mechanical energy initially is E0, then replace it and try to find v0 as v0 equals to the radical 2 E0 over m. Replacing the values, we can find that it is 1 meters per second. This is enough for this video. Please keep in your mind all the areas that we have mentioned before, and remember that during undamped free oscillations, the mechanical energy is constant, the kinetic energy, potential energy, elastic are constantly transferring to each other. The period of energies is equal to half that of oscillations. This is the end of part 4. Thanks for watching.